Okay, so, all right. So, most acid bases are reversible. We talked about the idea of reversible reactions in Chapter 9 with this idea of equilibrium, right? So, most acid-base reactions are not just one direction. They're reversible. So this changes a little bit about how we think about everything. So, consider this reaction that we just looked at. So, looking at this one, think about for a moment, you have to look what happens between the reactants and the products. What is my acid? Hopefully you said it was HCl, because the way you can tell it's an acid is that the chloride has the hydrogen here, but then over here it doesn't. It loses it. It lost the hydrogen. It gave it up to something else. So that makes this the acid. Ammonia, right, over here it's got an extra proton, right, the extra charge and then the 4 instead of 3. That makes it a base. It accepted the proton, right? We also have to take into consideration the fact that the reverse process is also happening, right? So, this process is happening at the same time, right? So while this forward process is happening, once we build up the products, we can actually go backwards. Now, so we have to think about this from the other perspective. Let's look at this from the backwards perspective. Once we get a buildup of these products, they're now going to act as their own reactants and go this direction. So, from this perspective, from the perspective of this reverse reaction, what's my acid? So look at what lost a proton from left to right. So it has to be something, when we're talking about what's the acid in the base, it has to be something on the reactant side, right? Because that's the thing that's doing the action, not the resulting thing. So the acid is ammonium, right? Because it goes from NH4 plus to NH3. It loses its proton. And then that makes chloride the base because it accepts the proton, right? So, in the first reaction, ammonia is the base, HCl is the acid, but if you look on the other side, the chloride is the base, and ammonium is the acid. So we can pair them up, right? So, NH3 and NH4 plus are a pair of an acid and a base. This one is the acid, this one is the base, right? You can tell because the acid is always going to have one more proton, right? And the relationship between them is when this acid loses its proton, it becomes this base. When this base accepts a proton, it becomes this acid. So they're related by having gained or lost an electron. That's the relationship between each other. The other pair is HCl and Cl minus. So HCl is the acid, chloride is the base, right? Because chloride can take a proton and become HCl. HCl can lose a proton and become chloride. So we call them conjugate acid-base pairs. And the definition is that they are a Bronsted-Lowry acid and base pair that differ by one proton. So if I take any acid, HNO3, right? When it loses a proton, what I get is its conjugate base. And its conjugate base would be NO3 minus. So I take away a hydrogen, and I give it a more negative charge because I'm taking away something that's positively charged. So this is a species formed when an acid loses a proton. Remember, it differs only by one proton. So H2SO4, its conjugate base is HSO4 minus. I don't take both protons away. And I'll talk about this in a little bit, but this is the acid, and here's its conjugate base. A conjugate acid, so if I take a base like NH3, its conjugate acid is NH4 plus. I just stuck an extra proton on there. So it's a species formed when the Bronsted-Lowry base gains a proton. Now, you might be asking, how do I know when the proton goes in front and the hydrogen goes in front and when it doesn't? So for things that are there's a little bit of just knowing your compounds here. But as a rule, things that are traditionally acids always have the acidic hydrogen out in front. Like, for example, there's a couple ways to write. So like acetate is C, what am I trying to say? C2H3O2 minus. Well, its conjugate acid is HC2H3O2. Why do I write this H out in front? Because it's acidic. It can be lost, right? So the conjugate acid of SO4 2 minus, right, is HSO4 minus, right? So I've gained a proton, and it gains a charge from that. Okay. Well, here. So try these. Whichever of these I haven't done already. Okay, so HSO4. Now, when I say write the conjugate base, it means that we are now considering this thing to be an acid, right? Because I get the conjugate base by an acid losing its proton. So HSO4, if it loses a proton, is SO4 2 minus. So that's the conjugate base. Right, the conjugate acid of NO3 minus of nitrite. So if I want the conjugate acid, then this is being treated as a base, so it gains a proton. Write the conjugate base of this. This is being treated as an acid. Remember, conjugate pairs only differ by one proton. So H2PO4 2 minus. And finally, write the conjugate acid. This needs to be a base, so H2C2O4. Okay. Now, you may have noticed something in there when I was talking about conjugate acid-base pairs. You may have noticed that, actually, I'm going to start a new, no, never mind, I'm not going to start a new one. I'll talk about amphoteric substances because it dovetails very nicely. So, amphoteric, or your book uses a different word that's actually a synonym. It's amphiprotic. They mean the same thing. So amphiprotic, amphoteric, they're the same word, or not the same word, they have the same definition. And it's a substance that can be an acid or a base. So you may have noticed in there something like HSO4 minus. So it has a negative charge. So most anions could take on protons to become acids, right? So what could happen is if this thing gained, actually let me do it this way. If HSO4 gained a proton, it could become H2SO4. So that means that this is acting as a base. It's accepting a proton, and this is its conjugate acid, right? But HSO4 also has a proton out here that it could lose, and it could become SO4 2 minus. So this is acting as an acid, and this becomes a conjugate base. Okay, so here's the deal. This thing, HSO4 minus hydrogen sulfate, is amphoteric or amphiprotic. It can act as an acid or a base. So, which is it? Which does it do? It totally depends on what it's paired up with. Basically, if something that's amphiprotic reacts with something that wants to give up a proton more than it does, then it'll act as a base and take a proton. If it reacts with something that wants a proton more badly than it does, then it'll act as an acid and donate it. So it all depends on what you're reacting an amphiprotic substance with. So water is amphoteric. So just like I said, so we know that HCl is an acid. If I react it with water, water acts as a base and takes the proton, because HCl is more acidic. And HCl, the meaning more acidic, by more acidic I mean it wants to give up that proton really badly. Water can also act as an acid. Ammonia is very basic. It wants a proton so badly and it takes it from water. So And this is kind of unfair. I mean, water is amphoteric, to be sure. It is amphiprotic. However, it is important to realize our definition, our understanding of what we call an acid or what we call a base, because water is the most common solvent, and most of the time we're dissolving things in water, our definition of what things are acids and what things are bases is based on, are they more acidic or more basic than water? Something we call an acid is capable of donating a proton to water. Something we call a base is capable of taking a proton from water. That's actually where the definition is based.